Welcome to the video lecture for section 4.3. In this section we will be looking at quadratic inequalities, specifically quadratic inequalities in one variable. So an example of this type of inequality might be something like x squared plus 2x plus 1 is greater than 0. We will get into how to solve both this type in two different ways, either graphically or algebraically. We'll look at the graphical approach first. So the idea behind the graphical approach, which is described on page 57 of the notes, is to think of the left-hand side, or the non-zero side, as a function. So we can think of this as f of x, and so we could interpret f of x as a graph. And the graph of this is going to look like a parabola. We can use the techniques from the previous section to graph what we have here on the left-hand side. And then we can find the part of the graph that is greater than 0 in this case. In other words, above the x-axis. So that's the part of the graph that satisfies this inequality, but we actually want to find the associated x values. In other words, we would like to find the part of the domain of this function for which its graph lies above the x-axis. So let's get started with this one as an example. X squared plus 2x plus 1. We need to graph it first. Now, I'm jumping the gun a little bit. With this type of setup, with this type of inequality, we want to write in standard form first. So set one side to 0. If that's not the case, then this approach is not directly applicable. So you want to get one side equal to 0 first, then graph the non-zero side. Okay. So how do we want to graph this? Well, we can go through all of our steps. We notice that this parabola is concave up because its leading coefficient, a, is 1, which is greater than 0. So this is a upward opening parabola. Then we can get into finding the vertex. Remember, the vertex has h and k as its x and y coordinates, and h is given by negative b over 2a. Well, in this case, b is 2, and a, we just said, is 1. So our x-coordinate of the vertex is going to be negative 1. And to find the y-coordinate, or k, we're going to plug negative 1 back in for x into our original inequality, or into our original function, as we're thinking of the left-hand side. So negative 1 squared plus 2 times negative 1, plus 1. That's negative 1 squared gives us 1. Negative 1 times 2 minus 2 plus 1. Alright, it looks like we end up with a y-coordinate of 0. Okay. So just to give a preliminary idea of what the graph of this parabola looks like, we've got our vertex at negative 1, 0, right there. This parabola opens upwards, so let me find the y-intercept as an additional data point. Alright, so if we plug in 0 for x, we're going to get 0 squared plus 2 times 0 plus 1, which gives us 1. So our y-intercept located at 0, 1. Right there. And so our parabola opens upward, passes through that point. We have our axis of symmetry. So we have this other point on the other side, negative 2, 1. Okay, so that's our parabola. Smooth it out a little bit. Alright, Now we go back to the original inequality and look at what we're trying to achieve. We would like our graph, or the part of the graph which lies above, and I say above, so strictly above, the x-axis. Alright, so let me graph this again, only copying down the parts that actually satisfy the inequality. Okay, so this piece off to the right lies above the x-axis. So does this piece coming off to the left. The only part of our graph which does not lie above the x-axis is that one point where our graph is on the x-axis. So every single point on this parabola, except for the vertex, is above the x-axis, and the x-coordinates associated with that are negative infinity up to -1, not including -1, union -1 to infinity. So the domain of the left-hand piece and the right-hand piece, any x value in either one of those intervals, causes the left-hand side to evaluate as a positive number and satisfy the inequality that we are starting with. So that's our general procedure. We will graph the parabola once we put it into that standard form with one side of our inequality equal to 0. Then we'll pick out the part of our graph which satisfies the inequality, whether it's greater than or equal to, less than or equal to, and we'll see a few of each of those examples. From there, once we know which part of the graph we like, we'll identify the domain of that part. The domain of that part is what is going to cause our inequality to be satisfied. So our solution, in this case, negative infinity to -1, and -1 to positive infinity, only excluding that one x value. Now, you can always go back and check if you're unsure of your solution set. You can't check every x value, but you can certainly try a few of them. If you plug in something from this interval into your original inequality, you'll see that it is satisfied. If we plug in -2, for example, we would get -2 squared plus 2 times -2 plus 1. That's 4 minus 4 plus 1, which is greater than 0, so that checks out. If we plug something in from the right-hand interval, something greater than -1, for instance, we could try 0. 0 squared plus 2 times 0 plus 1. That's 0 plus 1 is greater than 0. So that also checks out. Now, it's sometimes a good idea to check the x value that you exclude as well. So the only x value that we think is not a solution is -1. So what happens when we plug -1 into our inequality? Well, we get -1 squared plus 2 times -1 plus 1. That's 1 minus 2 plus 1. That's 0. And 0 is not greater than 0. So that's why we are excluding that x value. And that's as close as we can get to really verifying our solution. So here on the next page we see another quadratic inequality, still involving most of the same pieces. Here we still have x squared plus 2x plus 1, but this time our inequality is a little bit different. We're saying we want x squared plus 2x plus 1 to be less than or equal to 0. So we don't need to do any additional work here. We already know what the graph of x squared plus 2x plus 1 looks like. So -1, -2 are vertex at -1, 0. Our y-intercept and our other point to give this parabola some nice shape. Okay. So we're skipping over a couple of steps. We've already got this in standard form, and then we graph x squared plus 2x plus 1. So now the only trick is to pick which part of this graph satisfies the inequality. So if I think of f of x less than or equal to 0, what we're saying there is that the y-coordinates should be less than or equal to 0 on this graph. In other words, the point needs to lie on or below the x-axis. Well, looking at this graph, none of those points lie below the x-axis, but there is this one point, in fact the vertex of this parabola, which lies on the x-axis. So there is only one point that is a solution to this inequality, the point -1, 0. So our solution is x equals -1. That's the only x value that will satisfy our inequality that we were given. Now we already know from the previous problem that if I plug in anything other than -1, the left-hand side is greater than 0. Refer back to that example to see how we checked that very briefly. But when x was equal to -1, the quantity, the expression on the left, evaluated to exactly 0. So if we check x squared, or check -1 in this inequality, x squared plus 2 times -1 plus 1, my left-hand side is 1 minus 2 plus 1, which is 0, which is in fact less than or equal to 0. So I would say this is our only solution, based on the graph that we're viewing here. In our second example here, example B, we again see almost exactly the same setup as the previous two problems. We have the same expression on the left, and in this case we're saying greater than or equal to 0. So if I refer back to my graph, plot a couple of those points. Get our nice little curvy parabola. Alright, so I've skipped over steps 1 and 2. I've already got it in standard form. I've already graphed f of x. So now the only thing that I need to decide is which part of this graph satisfies the inequality. Which part of this graph is greater than or equal to 0. In other words, which part of this graph has y-coordinates of 0 or greater. Well, those are going to be the points on or above the x-axis. And we can see that this graph, in its entirety, lies on or above the x-axis. So the domain of the parts we want is exactly the domain of the whole graph, which is -∞ to infinity. All real numbers will satisfy this inequality. Alright, so that is how we handle these. We need to examine the graph, determine which parts of it we like, and then express the domain of those parts in interval notation. Alright, so here on our next page we have a similar type of problem. We would like to solve this quadratic inequality. We can tell it's quadratic because of the x squared term. There's no larger powers of x. This one is already in standard form, so we don't need to do any work preliminary to jumping into graphing. So I want to graph f of x equals x squared minus 4. Now we could go through all of the trouble of graphing this using the approaches from 4.2, but I think we might be able to save ourselves some time by looking back to chapter 3. Remember, x squared, our basic parabola, passes through 0, 0, 1, 1, 2, 4, and is even, so is symmetrical about the y-axis. So it contains all of these points on the other side as well. Okay, so that would be x squared. And to graph x squared minus 4, we would shift x squared down 4 units. So if I move every one of those points down, 1, 2, 3, 4, and move that one down 1, 2, 3, 4, and move 2, 4 down 4 units, and same with the points on the other side. Then we see the parabola we actually want to graph, x squared minus 4. Alright, so let me blow that up a little bit. X squared minus 4 contains all of those points, just kind of zooming in on this. Okay. So there we've got x squared minus 4, and all we need to decide now is which part of this graph are we being asked about? Does our inequality suggest? Well, looking at our inequality, we want points on this graph that are below, sorry, getting ahead of myself, are above actually, right? Greater than 0. So above the x-axis. Alright, so let me regraph and just include those points. Well, in between these x-intercepts at positive and negative 2, our graph is below the axis. We see that. But outside of those x-intercepts, we see our graph is above the axis. So this is the portion of the graph that we actually want. Now you can also achieve this same effect by maybe using a piece of paper or the side of your hand to cover up the part that you don't want, and then just state the domain of the part that you do. Now since our inequality is strict, we want to be above, not on, the axis, and that's why I'm excluding those zeros, those x-intercepts specifically. Every other point lies above, so I would say our intervals of interest are negative infinity to negative 2, and positive 2 to positive infinity. That's our solution set. Okay. Now if I flipped that inequality, if I said x squared minus 4 less than or equal to 0, well then I would want the other part of the graph. I would be interested in the x-intercepts specifically, because less than or equal to suggests on or below. So those points, negative 2 and positive 2, 0, and everything in between, that's the part of the graph that we like in this case, and the domain of that part is bracket negative 2 to 2, including both endpoints. Alright. Now these graphs have been relatively easy. I want to look briefly at one that might be a little bit more challenging. So here we have another quadratic inequality. This one is not in standard form yet. So this inequality we are going to have to manipulate to get one side equal to 0. And I can do that by subtracting 1 from both sides. So the inequality that we really want is 2x squared plus 8x minus 1 is greater than 0. Okay, so what I need to do is graph f of x equals 2x squared plus 8x minus 1, and then select the portion of that graph which lies strictly above the x-axis. Okay. So this one is not as easy to identify the graph as the last one. We need to go from ground zero and identify the concavity. Well, this parabola has a coefficient of 2 for the x squared term, so this is going to be concave up. In fact, this parabola is going to be narrower than x squared would be, since it's being stretched by a factor of 2. That may not be important, but it's always good to know everything you can about a parabola. Second, we'll identify the vertex. So we'll start with h, negative b over 2a, negative 8 over 4, that's negative 2. Then k, the y-coordinate, we can find by plugging negative 2 into our function. So 2 times negative 2 squared plus 8 times negative 2 minus 1. So 2 times 4 minus 16 minus 1, that's 8 minus 16 minus 1. So finally we end up with negative 9. Alright, and while we're at it, just a preliminary graph of this, our vertex negative 2, negative 9, and a parabola opening upwards, we are going to have x-intercepts and a y-intercept. So let's find those intercepts. And I'll start with the easy one. Let's find the y-intercept. Well, looking at our function, f of x equals 2x squared plus 8x minus 1, this is in standard form, so we can say our vertex is going to be 0c, which is 0, negative 1. So my graph up at the top is not very accurate, but it gives us a good idea of what we should expect to find. Alright, let's look at the x-intercepts. And remember, to find your x-intercepts, you're going to let y, or f of x, equal 0, and then solve the resulting quadratic equation. Okay, so I need to solve this quadratic equation, and that's going to be a little bit challenging. You might attempt to factor. Nothing great is coming to mind, so I'm going to go straight for the quadratic formula. Which tells me that x is equal to negative 8 plus or minus the square root of 8 squared minus 4 times 2 times negative 1. All of that divided by 2 times 2. So there's b squared, 4ac, all over 2a. And now we're just crunching numbers. So that's negative 8 plus or minus the square root of 64 minus 4 times 2 times negative 1. That's going to be positive 8 all over 4. So negative 8 plus or minus the square root of 64 plus 8 puts us at 72 all over 4. Now 72 can be written as 4 times 9 times 2, all over 4. So what I notice is we can pull the 4 outside as a 2, and we can pull the 9 outside as a 3, and be left with the square root of 2, all over 4. At which point I can cancel a 2 from everywhere, and we'll be left with our final, most simple answer for our x-intercepts, negative 4 plus or minus 3 root 2 over 2. So you may want to plug those into your calculator, which gives you two possibilities, 0.1213, and I'll round to 4 decimal places, although my answer goes on much further than that, and negative 4.1213. Now those are just approximations that are going to help me graph this parabola. My exact x values for the x-intercepts are going to be useful. The x-intercepts are located at negative 4 plus 3 root 2 over 2, 0, and negative 4 minus 3 root 2 over 2, 0. Remember, this is the smaller of the two x values. This is our negative 4 and change. And this one is the larger of our two x values, which is somewhere around 0.12. So if I plot my coordinates a little further, alright, and our vertex down here at negative 1, negative 9, oh, I'm sorry, that should be negative 2, negative 9. Our y-intercept we know is at 0, negative 1, and our larger x-intercept, we'll plot that at 0.12, might not be exactly to scale. Our smaller, negative 4.12, somewhere in this area. And so if I connect up my parabola as best I can, that is what 2x squared plus 8x minus 1 would look like. Might be a little curvier than that, not that pointy. Alright, so graphing this one was a little more challenging. And now we have to go back and remember that we want to be above the x-axis, and strictly above because our inequality is strict. So the part of our graph that we would like actually begins on the axis and goes up from there. So that part that we have circled, those are our solution segments. So what is the domain of those pieces? Well, the left-hand piece goes down to negative infinity and comes up to that left-hand x-intercept, which we got from negative 4 minus 3 root 2 over 2. We skip all of that area in the middle, and the graph portion that we would like on the other side, its domain is negative 4 plus 3 root 2 over 2 to infinity. Alright. So those x-intercepts are very important in this section. Once we put our parabola or our quadratic inequality into standard form, when we go to graph the parabola, the x-intercepts are going to define potentially the boundaries of our solution intervals. So you always want to try to find those if they exist. If they don't exist, then we may actually have a simpler situation to resolve, as we will see in the next example. So here we have a quadratic inequality. This one doesn't look quite like the others that we've seen. This one is not multiplied out. This one is part of it is factored. Let me begin by getting one side equal to 0. So I'll add 3 to both sides and see where that leaves us. X plus 2 squared plus 3 greater than or equal to 0. Now this doesn't look exactly like those forms that are in the notes, but we can actually make do with what we've got here. I'm looking at this parabola, and if we think of the left-hand side as f of x equals x plus 2 squared plus 3, then we can recognize this parabola is already in vertex form. And that may work out when it comes to graphing. So let's graph. Now what do we know about this parabola? Well, first, the leading coefficient a, we don't really have one, so we would say that a equals 1. So a being greater than 0 implies this parabola is concave up. And since it's in vertex form, we can immediately tell the vertex is going to be at -2, 3. So refer back to section 4.2 if that is a strange idea, but that is the nice thing about vertex form. Vertex form, y equals a, x minus h squared plus k. We can pick out h and k immediately if we know what we're looking at. So our vertex at -2, 3, this parabola opens upwards. Let's see what we're dealing with. -1, 2, 1, 2, 3. So our vertex right about there, and this parabola opens upwards. So we see this parabola lies entirely, strictly above the x-axis. And what are we trying to achieve? Well, if I go back to the inequality that we set up, we would like to be above or on the x-axis. Well, every single point on the graph of this parabola satisfies that. In fact, it goes one step better. Every point on this parabola is strictly above. So the entire domain of this parabola, our solution, is all real numbers, -infinity to infinity. Any x value you plug in will satisfy that inequality. Another way of thinking of this, going back to where we started, x plus 2 squared is greater than or equal to -3. Well, if I plug something in for x, I'm going to add 2 to it and then square the result. So no matter what is inside of these parentheses, when we square it, the result is going to be positive, or at least non-negative. The result may be 0 or larger. And that means that the result on the left is always going to be greater than -3. So this inequality is always true, and therefore our solution, -infinity to infinity, is valid. So that is a pretty exhaustive look at the solving by graphing approach. Now you can use all of these same techniques using the graphing calculator. If you were to graph, now again beginning by setting one side equal to 0, then you graph the left-hand or non-zero side and see which part of it satisfies the inequality that you're working with. So let's try that for this one. If we start from x plus 2 squared plus 3 is greater than or equal to 0, we're going to graph the left-hand side in our calculator. So if I go to my y equals screen, type in x plus 2 all squared plus 3, and hit graph, and you'll probably want to use a standard zoom for this problem. We can see that our graph exactly resembles the one that we came up with on paper. And so going to our inequality of interest, greater than or equal to 0, where is the graph on this screen, above or on the x-axis? Well, the whole thing is above, and so that gives us our solution, -infinity to infinity. Now for something else that we saw already, if we wanted to solve in the calculator, for example, that quadratic inequality x squared minus 4 is greater than 0. This is already in standard form, so I can go ahead and graph x squared minus 4. So going in and clearing out what we've got, x squared minus 4, and graph, and again the standard window should work. Now here I see that part of my graph lies above the axis, part of it lies below, and part of it lies on the axis. So my inequality of interest says we want the part above only, strictly above, the x-axis. Alright, well, to know where that's taking place, I need to know where it is on and below. So finding the x-intercepts, we see if we calculate the 0, I'll look at the left-hand 0 first, go a little bit to the left, and then a bit to the right, and then guess, somewhere in between. We see x equals -2. And on the other side, if I calculate the 0 again and scroll over, and give my left bound, go a bit to the right to give my right bound, and then guess somewhere in the middle, we see x equals +2. So the x-intercepts, the point where this left-hand side is exactly 0, are x equals positive and -2. So the part of the graph that lies above those coordinates, or above those points, is everywhere to the left, so everything below -2, and everything above +2. Alright, so that's how you would solve these using your calculator. That basically takes the work out of graphing the parabola by hand, but you still do have to approach it with the logic of the inequality in mind. Now that technique can also be adapted so that we don't actually have to graph. We can use the same concept of the x-intercepts being the points of interest and solve these types of problems algebraically. Now if you look in the notes, you'll see the steps outlining the algebraic approach. You want to begin in the same fashion by isolating one side being 0 and isolating the quadratic part of your inequality on the other side. From there, you would like to find the zeros of the quadratic side. So we'll look at this slightly new quadratic inequality. X squared plus 5x is less than or equal to 6. And we want to begin by putting it into standard form. So we'll move that 6 over and write this as x squared plus 5x minus 6 is less than or equal to 0. So in our process, we want to find the zeros of f of x equals x squared plus 5x minus 6. In other words, we want to find the x-intercepts of this function. So, if we let our function value be 0, 0 equals x squared plus 5x minus 6, I always like to try to factor if I can. That's one of the nicest ways of solving quadratics. And this one, it turns out, will factor pretty nicely. We'll need an x and an x. And then for my last pieces, for my constant pieces of these binomials, I need numbers that multiply to -6. So -2, +3, +2, -3, 1 and, or -1 and 6, 1 and -6. And I want a pair that adds up to 5. And I think -1 and +6 are going to be our winners. Alright, Well, now that we have this factored, we can set each piece equal to 0, x minus 1 equals 0, or x plus 6 equals 0. So we see that x equals 1, or x equals negative 6. Those are our x-intercepts. So those are going to be the boundaries of our solution set. So if we set this up on a number line, we'll plot those intercepts from low to high, negative 6 and 1. So what these x values represent are the points along the x-axis where our parabola of interest would cross the axis. Now we just have to determine in which regions is the parabola above and below the axis, and then pick the regions that satisfy the inequality of interest. So if we evaluate x squared plus 5x minus 6 using a test point within each interval that we've delineated here, that will tell us whether the entire function in that area is positive or negative. So I'll pick a test point here somewhere less than negative 6. I'll try negative 7. Actually, let's use an even nicer number to work with. Let's do negative 10. Really, any number in this region below negative 6 will work. So you can pick whatever number is going to be easiest for you to work with. Alright, well, negative 10 squared plus 5 times negative 10 minus 6, that's 100 minus 50 minus 6. That would be 44, which is positive. So we don't particularly care what the result is. We only care about the sign. Is the result going to be positive or negative? Another way that you can check this, if you've already figured out how x squared plus 5x plus 6, or minus 6 factors, we could think of this as the factors x minus 1, x plus 6, and plug in our test point. So negative 10 minus 1 times negative 10 plus 6, well, that would be negative 11 times negative 4, which is a negative times a negative, which is a net positive. Alright. Now in our middle region, some number between negative 6 and positive 1 is what's called for. I usually like to use 0 when I can. So if I test 0, 0 squared plus 5 times 0 minus 6 is negative 6, which is negative. I can also use the factored form. 0 minus 1 is negative. 0 plus 6 is positive, and the product of a negative and a positive is negative. So what that tells me so far is that to the left of negative 6, my parabola would be above the axis. In between negative 6 and 1, my parabola would be below the axis. Let's see what's going on beyond 1. So if I try x equals 2. Let's see, that would be 2 squared plus 5 times 2 minus 6. So that's 4 plus 10 minus 6. 14 minus 6 is 8. So that's positive there. So our parabola would be above in this region. Using the factored form, we could use 2 minus 1, which gives us 1, which is positive, times 2 plus 6, which is also positive, and the product of two positive numbers, regardless of what they are, is positive. Alright, so once I know the sign of the function in each of these parts of the plane, I can figure out which part I'm interested in. Well, going back to our inequality, we want x squared plus 5x minus 6 to be less than 0. In other words, or less than or equal to 0. So we want on or below. While our parabola, our function, is on the x-axis, it is 0, at the intercepts that we found. So we'll select those. And below is going to be where the sign is negative. So the negative region is all of this space in between -6 and +1. So I kind of like doing this number line argument because the number line translates directly into the interval notation, -6, +1, with brackets because we are including the endpoints because this inequality is non-strict. The zeros, the x-intercepts, are part of the solution, so those x values are part of the solution. So that's the algebraic approach. You begin by getting it into standard form, one side equal to 0. Then you find the intercepts, or you find the zeros of that quadratic side of your inequality, plot those on the number line, and then test each region. Pick a test point to the left of the leftmost 0, in between the zeros, and to the right of the rightmost 0, to see what your parabola is doing, whether it's positive or negative, in those regions. Once you know the signs, then refer back to the inequality to determine which sign is the one you want. In this case, we wanted to be less than or equal to 0, so we wanted the negative parts of the parabola. Let's look at one more of those just to see how those go. So here, we're actually going to go back and solve the first inequality that we looked at in this section. This time, however, we're going to do it algebraically. So first, we want to put it in standard form. One side is equal to 0, so we're good there. Now I want to find the zeros of this quadratic part. In other words, I want to find the x values for which this piece is equal to 0. So if I set x squared plus 2x plus 1 equal to 0, and then solve, I'll be able to find the zeros, and those are going to be my critical numbers. Now, x squared plus 2x plus 1, this happens to be a perfect square trinomial. This factors as x plus 1 squared. And if you don't believe me, you can always FOIL that back out. X plus 1 squared is the same as x plus 1 times x plus 1, which is equal to x squared plus x plus 1, which is equal to x squared plus 2x plus 1. So this is our factorization. And then I can say that x plus 1 equals 0, or x plus 1 equals 0. It's kind of silly to say it twice, seeing as our only solution is x equals -1. So the only critical number, the only number that's actually on our number line when we go to solve this algebraically, is going to be -1. And if you remember, when we solved this graphically, our only x-intercept was located at -1. Remember, it was the vertex of this parabola. So that's the only point, or the only x value, for which this left-hand side is 0. So if I plot -1, now I need to pick test points on either side of this, and I'll plug those into x squared plus 2x plus 1. So a good test point somewhere to the left of -1 might be -2. So we would evaluate -2 squared plus 2 times -2 plus 1, which is 4 minus 4 plus 1, which is 1, which is positive. Then we'll pick a test point somewhere to the right of -1. I think 0 is a good candidate. So if I evaluate 0 squared plus 2 times 0 plus 1, that'll leave me with 0 plus 0 plus 1, which is also positive. Alright. Now referring back to our inequality, now that we know the sign of our function, pretty much know its behavior graphically. It's going to be above the axis everywhere to the left of -1 and everywhere to the right of -1. The only place it's on the axis is at x equals -1. So let's go back and see what we're trying to accomplish. Well, we want to be greater than 0, so we want to be above the x-axis. In other words, we want to be positive, and strictly positive. We don't want zeros. So our solution won't include that x value, but everywhere to the left and to the right, we have exactly the conditions that we're hoping for. So everywhere to the left and to the right of -1, our quadratic evaluates as being positive, which is what we are shooting for. So I would say our solution intervals are -∞ to -1, excluding -1, and -1 to positive infinity. And if you refer back, that is exactly the conclusion that we came to graphically. So that's how you would handle this type of situation where you don't necessarily have two nice x-intercepts. You can still plot your solutions to that second step, finding the zeros, plotting them, and then picking something in the test interval to determine which part of the interval satisfies or causes your quadratic to satisfy the inequality. So in this case, we had one critical number to plot. Let's see an example that's slightly different. Okay, so here we have one last quadratic inequality. This one is already in standard form, so we can proceed right to finding the zeros of the left-hand side. Okay, so if we set this equal to 0, we get x squared plus 1. Now this quadratic equation is a good candidate to use the square root method, since we only have an x squared term and a constant. So what I need to do in this case is isolate the x squared term. So if I subtract 1 from both sides, I get -1 equals x squared. And then I can square root both sides and get x equals the positive or negative square root of -1. In other words, x equals positive or negative I. Now there is no way for me to plot positive or negative I on a real number line, which means that my graph, if I were to graph x squared plus 1, this graph doesn't actually have any x-intercepts. So there's only one possibility. My graph is on one side of the axis or the other strictly and never crosses the x-axis. So my number line is going to be pretty boring. If I test some value, I need to pick some value in the real numbers. So if I test x equals 0, let's see how that turns out. Well, 0 squared plus 1 is 1, which is positive. So this graph is above the x-axis everywhere, no matter what x we plug in. If we plugged in 2 or 5 or 50 or -1,000, we would square that value and then add 1. We'd get a positive plus 1. So this graph should be positive over its entirety. We can kind of see that by just sketching the graph really quickly. X squared plus 1 is going to look just like x squared, but shifted up 1 unit. Okay. So on our number line, we've figured out that this parabola is positive everywhere, and strictly positive. There are no x-intercepts. So going back to the inequality we're hoping to satisfy, remember we want x squared plus 1 to be negative. We're looking for a minus down here, and we don't get one, which tells me that there is no solution. And that can certainly be the case. If I ask you to find the parts of the parabola x squared plus 1 that lie below the x-axis, there's no solution. It doesn't ever happen. Okay. Now it's worth mentioning that there's often some confusion between quadratic inequalities and back in chapter 2 when we saw linear inequalities in two variables. Our solutions in this section are going to be numbers, x values only, whereas our solutions back in chapter 2, sections 2.3 and 4, the solutions there were points, right? There is no y value involved in this inequality, so there should be no y value in our answer. Additionally, that means that there should be no shading involved. We're not looking at regions of the plane. We're looking at sections of a graph and the x-coordinates that correspond to those sections. Alright, so that is all for section 4.3. Go ahead and take a look at those homework assignments and bring any questions you have to class.